Well, that was inconvenient, wasn't it? I'm sorry. All right, today we are going to do Chapter 8, Acids and Bases. We will talk about hydrogen bonding, the process of autoprotolysis, ionization of molecular compounds, strong acids and bases, conjugate acid-base pairs, neutrality and the pH scale, and finally, pH calculations. Now, for pH calculations, you should take your calculator out, get it warmed up, because doing these calculations is not always intuitive. This is my calculator. What you're looking for is a button called log and a button called 10 to the x, okay? Just to make sure you got it and it's working, type in 4,000. Hit the log button, you should get 3.602. Leave the 3.602 up on your screen and hit 10 to the x. It should go back to 4,000. Once again, the calculations are not totally intuitive, and probably haven't used your log button very much in the past. All right. Last chapter, we talked about polar covalent bonds. We said that water had two polar covalent bonds at a 109-degree angle. This causes a molecular dipole, where this is the positive end of the molecule, and that's the negative end. We see this in the electrostatic potential map. Big blue bottom for positive, nice red top for negative. The fact that water is polar is the thing that allows it to do things like dissolve ionic compounds. Sodium chloride. The chloride ion is surrounded by waters with the positive ends pointing in. The cation is surrounded by water molecules with the negative end pointing in. This disperses the positive and negative charges, making them stable in solution. Well, I contend that if water is polar and can interact with ions, water should also be able to interact with itself. The interaction between adjacent waters forms what's called a hydrogen bond. Basically, we bring another water up to this, we form a partial covalent bond where we actually share part of the electron cloud from one water with the positive end of another one. We have another hydrogen over here. We can bring another one in and do the same thing. Likewise, we have a negative end sticking up here. We can bring a third one in and form a hydrogen bond up here as well. Quite obviously, because water has three polar sections, we can do this indefinitely. On the very simplest of scales, water is surrounded by at least 4 water molecules, and again, all of these form hydrogen bonds. This is a calculation of a cluster of water. You'll see this oxygen here is bonded to this guy, here's the hydrogen, and this guy. Note in the calculation, see these things? This oxygen is basically swallowed that hydrogen, hasn't it? It's darn near as strong as this covalent bond. In reality, it's only about 5% of the covalent bond. But there are so many of them, this is a huge force. There's a nice dynamic movie showing hydrogen bonds of a section of water. The little purple things that keep appearing and disappearing are the water of the hydrogen bonds. So imagine this happening, a billion times faster. This is what a water cluster really looks like. If you look at this closely, you'll see that all of these are not just simple water molecules. There are some in here that are missing a hydrogen, something like this. There are some that have 3 hydrogens. We'll look at this and explain how this happens. This is the process of autoprotolysis. In autoprotolysis, we take 2 water molecules that are hydrogen bonded. This is the hydrogen bond between the 2, hydrogen and an oxygen. This hydrogen bond is sufficiently strong that if either of these gets a little bit of extra energy, somebody bumps into it or whatever, this hydrogen can actually dissociate from its oxygen, travel along the hydrogen bond to the adjacent water. When we do this, we form a pair of ions. This is called the hydronium cation, and this is the hydroxide anion. Now, these are still hydrogen bonded. We can return this to where it came from, and we're back to having 2 hydrogen bonded waters. In reality, this process goes on very, very rapidly, 10 to the 6 times per second. The bottom line here is that anytime you have absolutely pure water, the concentration of hydronium and hydroxide will always be there. And at room temperature, 25 degrees, the concentration of both of these is 10 to the minus 7 moles per liter. Bottom line here, pure water, concentration of hydronium and hydroxide are both 10 to the minus 7 molar. That's due to autoprotolysis. In the last chapter, we talked about non-electrolytes. This is pure water. This is our little probe down in the pure water. Instead of it being 0, as you might predict, in fact, it has a value. It's small, but it has a value. That's due to hydronium and hydroxide from autoprotolysis. Any questions? Well, what we've done here is to generate 2 ions. I showed these as being hydrogen bonded. This is the hydronium ion, H3O+, and this is hydroxide, OH-. These are very highly charged. The only reason that these can exist in solution is that water can stabilize the charge. Now, last chapter we looked at a cation being surrounded by water and the water dispersing the charge. This is the hydronium ion and its electrostatic potential map. If you turn this on its side, you can see the extent of the positive charge down here on the bottom. If we take this cation and surround it by waters like we did in the last chapter, again, the electrostatic potential map for the entire surface. Here's our cation in the middle. The whole surface looks something like this. You'll note that here where the oxygen is, it used to be bluish. Now we've replaced it with something that is, let's go back to that picture, with something that's actually slightly yellow. Now water does not travel in sections of 4. We saw that. It's very dynamic. There are lots of water molecules involved. This is the same operation done with a hydronium ion in the middle, surrounded by 8 adjacent waters. We'll do this in a single layer. Remember, in reality, we would have waters above and below to help out in this process. But here's our hydronium ion. If we calculate the electrostatic potential map, the hydronium ion is here. You'll see the charge is essentially totally gone. And our oxygen is still up here, bright red. Remember, it used to be barely greenish. Amazing the way water can disperse a charge. This is why autoprotolysis works. Any questions? All right. If water can cause the ionization of an adjacent water, what does it do with the polar covalent bond? If the bond is sufficiently polar, it can break the bond just like it did for water. Remember HF. We did this last chapter. We said that this is a very polar covalent bond. If we take and bring a water up next to it, oops. Come on, water. There it goes. It can, of course, hydrogen bond here. What you're looking at is oxygen bonding to the polar end of HF. Just like happens in the autoprotolysis, if either of these gets just a tiny touch of more energy, this hydrogen can leave the fluoride and go over here and bond to the oxygen. What we have done is taken HF in water, we have made hydronium ion and fluoride anion. Just like we saw with water itself, this reaction can go back as well. When we have a reaction that goes forward and goes backwards at the same time, very, very rapidly, in chemistry, we refer to that as an equilibrium. We show that with a special set of arrows, one going forward, one going back. What this tells us is that this reaction goes back and forth, again, 10 to the 6 times per second. So very, very rapid transfer of the proton back and forth to water. We would call this the equilibrium ionization of HF. Now, the products of this are hydronium and fluoride anion. HF, or basically anything which makes hydronium ion in solution, is termed an acid. Again, if you could ionize, break the bond, and make hydronium, HF would be considered an acid. Oops. There's a theory, there are actually several theories describing acid-base theory. Bronsted has one, Bronsted acid-base theory simply describes the proton donor as being a Bronsted acid. The proton acceptor is a Bronsted base. Acid, base. We'll see there's another nomenclature as well, and that's coming up in just a minute. There are two classes of acids we'll deal with. One is called a strong acid, and one is called a weak acid. Basically, the difference has to do with the rate at which this goes forward and it goes back. If it goes forward much, much faster than it goes back, then you get lots and lots of hydronium. That's a strong acid. If it goes backwards faster than it goes forward, you have very little hydronium, and that's a weak acid. We are going to focus on strong acids. In general chemistry, you will do an awful lot of work with weak acids. Any questions? All right, strong acids, such as HCl reacting in water to give hydronium and chloride. This dissociation reaction goes very, very rapidly in the forward direction, very slowly in the back direction. The ratio of unionized to ionized is roughly 1 billion to 1. So everything is going to be hydronium and chloride. As shown in this little movie, again, this represents HCl, which is a gas. When the HCl gas goes into water, it very rapidly will dissociate, essentially completely, to give hydronium and chloride anion. Now, the one thing that is wrong with this little animation is the back reaction does exist, doesn't it? So we have to show that somehow. There's an undissociated one, but remember, the ratio of this to these guys is 1 billion to 1. Strong acid. An example of a weak acid. This is acetic acid. We've seen it before. It will ionize to form acetate anion and hydronium. But a weak acid ionizes very little in solution, so we put this stuff in water. We will get one of these every now and then that dissociates, and then boom, goes back. So the ratio here is roughly 100,000 to 1 for the one that's ionized. That's a weak acid. Any questions? All right, strong acids that we typically use. We've seen hydrochloric acid. In water, it gives hydronium and chloride. Nitric acid, we've used that in the lab. It causes brown spots on your skin. Don't touch it. It gives hydronium and nitrate. Perchloric is one that we haven't used in lab yet, but that ionizes to give perchlorate and hydronium. This is perchlorate with a hydrogen stuck on one of the oxygens. This is nitric acid. Again, hydrogen is on the negative oxygen. Because all of these give only 1 mole of hydronium, they're also referred to as monoprotic acids. Now, protic refers to proton, right? That's because when we get the ionization, the hydrogen is transferred as a bare, naked proton. No electrons. So this is proton dissociation. Everybody's favorite acid, however, has to be sulfuric. This is sulfate with, again, 2 hydrogens attached. It can lose these in steps. The first step forms hydrogen sulfate. The second one comes off in the second step to form sulfate, 2 moles of hydronium, called a diprotic acid. There's one triprotic that we use in lab, and this is phosphoric acid. This is phosphate, PO4 minus 2, with 3 hydrogens attached. Minus 3, I'm sorry. Any questions? Well, I said that there was another set of nomenclature that we would use aside from Bronsted acid, Bronsted base. This is conjugate acid and conjugate base. Really, it's fairly simple. A conjugate acid is a thing that loses the proton, typically to water, and it forms the conjugate base. The conjugate base is what is left over after we donate the proton. Simple way to remember that. For nitric acid, this is the Bronsted acid, that's the Bronsted base, okay? But for nitric acid, this is the acidic form, we'll call this the conjugate acid. Once it donates or loses its proton, it forms nitrate, which is called the conjugate base. The leftovers. Any questions? Conjugate base typically has 1 less proton and 1 more negative charge. That's another way to remember it. Okay. Once again, this is the Bronsted acid, Bronsted base. The conjugate base is what's left over after you lose the proton. So let's just look at a set and see if we can identify conjugate acid-base pairs. For HCl, the thing that's going to donate is HCl itself. When we lose the proton, what are we left with? Chloride. This is the acid form. This is the base. Conjugate acid, conjugate base pair. Sulfuric acid, again, can do it twice. When it loses the first proton, it goes from H2SO4 to HSO4 minus. This is the acid form. This is its conjugate base. When it loses the second proton, you go from hydrogen sulfate to sulfate. This is the acid form, and this is its conjugate base. Now, like I said, typically this happens in water, but ammonia can actually serve to ionize things as well. That's why oceans of liquid ammonia on distant planets actually could support life. Not quite the way we know it, but they could support life because ammonia can function, do a lot of the things that water can. In this particular reaction, nitric acid is the acid form. It loses its proton to form nitrate and ammonium. This is the conjugate acid. This is the conjugate base. Okay? On an exam once, I put this reaction, but I wanted to know the conjugate acid-base pair for the reverse reaction. Remember this going back and forth. Well, look at this reaction this way. Who is the proton donor? Ammonium is. After it loses its proton, what are we left with? Ammonium. This is the acid, this is its conjugate base for the reverse reaction. Any questions? Well, good. There's a tutorial called Conjugate Acid-Base Pairs. Looks something like this. Here we have two unknown fields that you enter structures. Again, you just write them out. Don't worry about super subs or charges. And when we look at this, we have something ionizing to give fluoride anion and water. So you ask yourself a question. What is the conjugate acid of fluoride anion? What loses a proton to form F minus? Well, it's got to be HF. What is it donating it to? What's the Bronsted base? Well, it's the conjugate base of hydronium. That would simply be water. Now, when you do this, both on my website and on Blackboard, do them in the order of the other half of the equation. So if you put water here, HF there, it would be wrong. So do it in the right thing. Fluoride first, water second. Do another. Chlorate plus hydronium gives what and what? Well, the acid form here is going to be hydronium, isn't it? It's going to donate a proton to chlorate to form something. So what is the conjugate acid of chlorate? What is formed when this gains a proton? It's simply HClO3, chlorous acid. When water loses its proton, what is its conjugate base? What's formed? If we take a proton off, we get water. Any questions? This one's a little confusing at first, but because we have two proton donors here, don't we? But hydronium is a much stronger acid than hydrogen sulfite, sorry. So this is going to be our proton donor. This is going to be our Bronsted base. So when hydrogen sulfite picks up a proton, you form sulfurous acid. When water loses its proton, you get water. Any questions? Blackboard works the same way with this one. Well, if we have things called strong acids, it's only fair that we have strong bases as well. A strong base is something like sodium hydroxide. Again, the criteria is that when you put it in water, the equilibrium lies 99.99999% on this side. So very rapid dissociation, very slow going back. If we have a strong base with hydroxide, it can react with hydronium. We transfer the proton from the acid to the base, and what do we get? We get water. This is not surprisingly called an acid-base reaction. Now look at this equation. This is the autoprotolysis equation, just written backwards, isn't it? Think about this equilibrium. We know that this equilibrium is such that we have 10 to the minus 7 moles of this, 10 to the minus 7 moles of that. So obviously, this reaction goes very slowly this way, very rapidly back. Same thing happens here in reverse. This is very rapid, very slow. So once we neutralize the acid and base by reacting with each other, we're left simply with pure water. Acid and base react to make neutral water. Here's a little cartoon showing that. This represents HCl and water. HCl forms hydronium and chloride anion. This represents sodium hydroxide. If we take and mix these together, as soon as they get in solution together, hydronium will transfer a proton to hydroxide, and we're left with water. In fact, the only thing in the solution now is sodium chloride. A strong acid reacting with a strong base gives a salt and water. Any questions? All right, let's look at some simple test questions. On this list of substances, which one is an acid first, followed by its conjugate base? Now remember, the acid simply loses a proton, and what's left over is the conjugate base. Well, the first one, that's silly because if this loses a proton, there's nothing there. That one's out. Going from ammonia to ammonium, we've gained a proton, haven't we? Hydrogen phosphate dianion to dihydrogen phosphate anion. Again, we've gained a proton. Hydrogen carbonate can lose the proton to form carbonate. This is the correct answer. Once again, in this last one, acetic acid has gained a proton to form protonated acetic acid. This question is confusing because it has too many words. We have hydrogen carbonate plus water to give carbonate and hydronium. Okay? Which of these is correct? Hydrogen carbonate is an acid. That's true. Water is the conjugate base. No. Water here is a bronzite base. Hydrogen carbonate is still an acid. CO2 minus, CO3 minus 2 is this guy. It is its conjugate base. When we lose its proton, the acid loses the proton to form the conjugate base. So this is the correct one. Hydronium is an acid. Hydrogen carbonate is its conjugate base. No. Conjugate base here would be water. Water could be regarded as an acid, but it would not form CO2 minus CO3 minus 2 as its conjugate base. And finally, this one, the same thing. We start with this, lose the proton, form the base. One more. Conjugate acid of hydrogen sulfate monoanion is what? So this is the conjugate base. The conjugate base will pick up a proton to form the conjugate acid. So hydrogen sulfate plus a proton gives sulfuric acid. Acid, base, pair. Any question? All right. Just a bit ago, I said the words strong acid reacts with a strong base to form neutral water, right? What do we mean by neutrality? Because remember, anytime you have pure water, you always have 10 to the minus 7 molar hydronium and 10 to the minus 7 molar hydroxide. They're always there in pure water. So when we speak of a neutral solution, we know that it's mostly water with just a tiny bit of this stuff in there. The tiny bit of this stuff is 10 to the minus 7 molar. If you wanted to calculate hydronium ion concentrations and whatever, you would have to use very, very small numbers to do so. A long time ago, that was considered inconvenient. So, a Danish chemist named Sorensen, looks like a Danish chemist, right, came up with the concept of pH. pH he defines simply as the negative log of the hydrogen ion concentration, or hydronium ion concentration. Negative log hydronium ion concentration is called pH. Quite often, you will see this not written as hydronium, just minus log H plus. Just shorthand. All right. What does the log thing do? What is a logarithm? They used to teach that in 7th grade. But these days, we have calculators, and they might have just skipped the concept totally. The little p in front of pH stands for negative log. A logarithm. Base 10 logarithm is a number. It's number in 10 raised to some exponent. Once again, if you take your calculator, type in 3,000, hit the log button, you should get 3.477. If you now hit 10 to the x, that's 10 to the 3.477, you should go back to 3,000. The logarithm of 3,000 is simply 3.477. It's that exponent. If we multiply 10 by 10, that's 10 squared. The log of 100 is 2. If we multiply 10 by 10 by 10, that's 10 to the third. Log of 1,000 is 3. If we add 10 to the 2.5, we get 316. Again, take your calculator, enter 316, hit log, and push equal. You should get 2.5. Go to your 10 to the x button. Do 10 to the 2.5. You should get 316. It's simply the exponent of 10 that gives the number. Now again, the logic here was that this is simpler than writing out all the exponents. It's a little confusing sometimes because you're not familiar with logs. Once again, little square brackets here is shorthand for concentration of the compound. This is hydronium ion concentration, and so is this. All right. We said neutral water, hydronium was 10 to the minus 7 molar, right? If you take your calculator and you type in 10 to the minus 7 and hit log, it's just the exponent, so you'll get minus 7. Remember, the pH is the negative log, so we multiply that by minus 1, and we get 7. The pH of pure water is 7. That's where that comes from. pH is 7 because hydronium is 10 to the minus 7. If we have an acidic solution, hydronium will be less than 7. If we have a basic solution, hydronium will be over 7. pH will be over 7. This is important. Make sure you know this. pH less than 7 is acidic. pH greater than 7 is basic. All right, we had strong acids. I said, therefore, we had to have strong bases. That's only fair. If we have a pH scale, it's only fair that we also have a pOH scale. Exactly the same. pOH is simply the negative log of hydroxide ion concentration. Okay. In neutral water, hydronium and hydroxide are both 10 to the minus 7. If we were to take the concentration of hydronium and multiply it by the concentration of hydroxide, we would get 10 to the minus 14. In fact, any hydronium ion concentration multiplied by the hydroxide ion concentration will always be 10 to the minus 14. Always. under all conditions at room temperature. Now this is useful because if you know the concentration of one of these, you can use 10 to the minus 14 as a constant and calculate the other. There's also a cute trick we can do. If we take the negative log of everything in this equation, the negative log of hydronium is simply pH. The negative log of hydroxide is POH. And the negative exponent here of minus 14 is plus 14. Under all conditions, pH plus POH always equals 14. So two things to remember. Hydronium times hydroxide is always 10 to the minus 14. That's a constant. pH plus POH is always equal to 14. So if we know a pH, subtract it from 14, you get POH. Simple as it can be. Let's just do one quick example. We know that hydronium times hydroxide is 10 to the minus 14. If I tell you that I have a hydroxide ion concentration of 5 times 10 to the minus 8, what is hydronium? What you would do is simply define hydronium, take 10 to the minus 14 divided by hydroxide, 10 to the minus 14 divided by hydroxide. This is hydronium. And again, if you take hydronium times hydroxide, you get 10 to the minus 14 under all conditions. Question. All right, let's just talk about pH a little bit. Stop doing calculations for a minute. Neutral water, pH 7. Hydronium, 10 to the minus 7 molar. Blood, sweat, and tears, a little basic, about 7.3. Ammonia or bleach, up here around 12 or 13. And 1 molar sodium hydroxide would have a pH of 14. Likewise, pH at 14, hydronium 10 to the minus 14. Going to the acid side, bad coffee, about 5. Tomatoes, 4.5. Wine, 3 to 4. That's really red wine vinegar. Bad wine is even worse. Stomach acid, about 1.5. Really strong acid. It's amazing the stomach just doesn't dissolve itself. And finally, 1 molar HCl, pH is 0. Again, hydronium would be 1 molar. The log of 1 is 0. How do we measure pH accurately? Well, we use something called a pH meter. It looks like this. You have a probe. You stick it in your solution. The probe is designed so that you have a very, very thin glass membrane. Looks like this. You have a solution inside, and of course it's down inside your solution. Depending upon the hydrogen ion concentration, that sets up a little tiny electric potential across the edge of this probe. Now, this is a thin glass membrane, I said. It's about as thick as a human hair. So it's very thin, which means it's also very fragile. So if you take it and you shove it into a beaker, as soon as it hits the bottom, it is likely to break. Now, because of that, you probably won't use something that looks like this ever. They have them that are shielded, whatever. When I was at UIC in our research lab, we had, of course, the bare naked ones because they were very, very accurate. But they also cost about $1,000 each. When you get a new graduate student in lab, you can count on the fact that they will break at least 20 of these in their first month or so. Graduate students can be very expensive. But again, you won't use this. Instead, in the labs, we typically use this. pH paper doesn't break. It's an amazing thing. Not nearly as accurate, but you take this little green strip, stick it in your solution, it'll turn dark blues all the way to red, depending upon the pH. So it's an engineering marvel, really. The paper is impregnated with what's called indicator dyes. An example is the organic compound phenolphthalein. That's the organic structure. In an acid solution, phenolphthalein is colorless. In a basic solution, at about 8-ish, it changes, starts becoming pink. This is the one that is commonly used in the lab. In general chemistry, you would use this a great deal. Somebody came up with the mixture of these sorts of dyes to come up with the paper. Now again, that's an engineering marvel, right? Well, not quite such a marvel, because somebody beat us to it. Red cabbage. If you take red cabbage, swoosh it up in a blender, you get red cabbage juice, right? If you take red cabbage juice and make it acidic, it goes beautifully red. Neutral is purple, as you can see. As you make it more basic, it goes from blue to a disgusting green. You can actually take cabbage juice and use it as a pH indicator. Red to blue. This is important if you happen to be a cook. If you take red cabbage, chop it up, saute it in a pan, you get something like this. Tastes great, looks appetizing, whatever. If you want to be a little extreme, however, you can take your saute pan and drizzle in a little bit of vinegar to make it acidic. When you do, it turns bright red. Halloween is coming up, right? If you want to really be disgusting on Halloween and you're making red cabbage, add a little bit of baking soda to it. That's sodium hydrogen carbonate. It makes it slightly basic. What's it look like? Disgusting green. Now these all taste the same. But this is perfect for Halloween. It's disgusting. Any questions? Well, in 110, we don't do this in the lab, but in general chemistry, they live by what's called titrations. So I'm just going to introduce the concept here. In a titration, you'll have two solutions. In this particular example, this is an acidic solution. This is basic in the diuretic. What you're going to do is you're going to measure your starting volume here. In this case, I said 10 mils. You are going to add this to the acids. And to the acid, we've added some phenolphthalein. Now remember, this is colorless in the acidic solution. As we dribble, we open the stock pot, the stuff dribbles in. When we hit neutrality, we get the color change. So you stop it. You have a final volume and an initial volume. You subtract this, that gives you a volume, right? In this example, we know the concentration here, but we didn't know the concentration of the acid. But we know its volume. Concentration times volume is moles. This tells us the number of moles of acid there must be in our unknown solution. Called a titration. Again, it's a standard general chemistry laboratory experiment. Any questions? All right, let's do the calculation here. We have a solution. We measure its pH, 7.23. I say to you, what is the hydronium ion concentration? Well, we can do that because we know that pH is simply the negative log of hydronium ion concentration. Simply the negative log. First thing I would like to do is get rid of the negative sign from this side. Let's move it to this side. We can do that by multiplying both sides by -1. So we get minus pH is log hydronium ion concentration. Next, we're going to do something called taking the antilog. The antilog is just the opposite of a log. Remember, we said logs were just exponents. So this is going to be the antilog of minus pH is 10 to the minus pH. The antilog of a log is simply 1, so this becomes simply hydronium. This is a very important equation. I would write this on my 3x5 card if I had one. 10 to the minus pH is hydronium. We substitute. 10 to the minus 7.23 will give us hydronium. Now, I take my calculator. Oh, when I was a child, we didn't have calculators, did we? We had volumes like this. Every science book had a half-inch set of pages at the back with log tables. And we would sit and look it up. Look up the logarithm for all these things. Don't have to do that now. You have a calculator. This is mine. Here's my log button. That's what I'm interested in. Here's 10 to the x. So we know that 10 to the minus 7.23, type in your minus 7.23, hit inverse 10 to the x, you get this number. 5.89 times 10 to the minus 8. That's all you have to do to find hydronium if you know pH. 10 to the minus pH is hydronium. All right. Here are some. If I tell you the pH is 4, what's the hydronium? Well, you don't even have to use your calculator for this one. 10 to the minus pH is 10 to the minus 4. So our hydronium, 1 times 10 to the minus 4. If I tell you the pH is 12, what is our hydronium? 10 to the minus pH. Or 10 to the minus 12. Now we have to enter and use our calculator. 5.5. Again, take your calculator, type in 5.5, change its sign, minus 5.5, 10 to the minus 5.5, 3 times 10 to the minus 6. 1.32. This is simply going to be 10 to the minus 1.32. Type it in, hit 10 to the x, 4 times 10 to the minus 2 molar. Again, back at our lab, this is the accuracy that we used to get on our pH meters, the $1,000 probe. But the operation is still the same, 10 to the minus 7.05567. And we have all these significant figures. Look at this list of pH values. Test your memory here. Which of these solutions is acidic? Remember, acid, pH is less than 7. Base, pH is over 7. So this is less, that's less, that's less. This is just a little bit over, but it's still basic. Any questions? Well, let's do this calculation backwards in. We know the hydronium ion concentration. What is the pH? Remember, pH is simply going to be minus log of hydronium. This is our hydronium. So what you're going to do is simply take the log of 7 times 10 to the minus 7. You type it in. Hit log minus 6.15. We have a negative sign in front, so that gives us a positive value of 6.1523. The other important question or equation to write on your card is this guy. Make sure you know minus log hydronium as pH. All right, well, let's do another set then backwards. We have hydronium ion concentrations, we want pH. Anytime it's even, 1 times 10 to the minus 4. You can do that in your head, right? The log of 10 to the minus 4, change the sign, pH is 4. Five times 10 to the minus 4. You simply type in 5 times 10 to the minus 4, take the log, change the sign, 3.3. .37 times 10 to the minus 8. Type it in, hit the log button, change the sign, 7.86. This next one was actually on an exam, okay? 7 times 10 to the minus 7 molar. What's the pH? Most of the class said pH was 7. There's so many 7s in the problem, right? Of course it's not. 1 times 10 to the minus 7 would be 7. If you type this in, hit log, change the sign, 6.15. Slightly acidic. And finally, 4.61 times 10 to the minus 5. Type it in, hit log, change the sign, 4.33. Any questions? Just takes a little bit of practice. And in this course, how do we practice? Well, we do tutorials, don't we? This is pH 1, okay? In pH 1, you're going to try to find a pH, and you're typically given hydroxide, or you're trying to find hydroxide, and you're given a hydronium ion concentration. So we have to do 2 calculations. We have to take this number, hydroxide, 10 to the minus 14, and get hydronium. Take its negative log and get pH. Now let's see how we do that. Remember, all conditions, hydronium times hydroxide is 10 to the minus 14. And again, under all conditions, pH plus POH is 14. You have all that written on your card as well. Running out of room on your card already. So, 10 to the minus 14 divided by hydroxide is going to give us hydronium. We're going to take our hydronium, take its negative log, and get pH. 10 to the minus 14 divided by the hydroxide that was given in the problem, 1.6 times 10 to the minus 4. Type it in, hit log, change the sign, 3.79. Let's do it again. Here we're looking for POH, and we know hydronium. Again, hydronium times hydroxide is 10 to the minus 14. pH, POH is 14. So we're going to take 10 to the minus 14 divided by the hydronium. That will give us hydroxide. take its negative log, we get POH. Ten to the minus 14 divided by hydronium gives hydroxide. It's 3 times 10 to the minus 12. Type that in, hit log, change the sign, we're at 11.46. That is pH 1. pH 2 is a table. Table has 4 slots. You're given one thing, you fill in the rest. Here we are given pH, but we remember pH plus POH is always 14. If we start with pH 10 to the minus pH is hydronium, we have hydroxide, 10 to the minus hydroxide, or minus, POH is hydroxide. So that's how we're going to do it. So here's what we have. POH, pH minus 14 is POH. That's the numbers. We get 3.17. 10 to the minus pH is a pH. Get this, type it in, get 10 to the x, 1.48 times 10 to the minus 11. We know POH, we can do the same thing. 10 to the minus POH, 6 times 10 to the minus 3. Now every time you hit new problem, you will get a missing or you get a known in a different category. Let's just do one. If we're given hydronium, we can take 10 to the minus 14, divide it by that, get hydroxide. Take log of that, change the sign, get pH. Log of this, change the sign, get POH. So here's what we have. 10 to the minus 14 divided by hydronium. There's the numbers. We're at 8 times 10 to the minus 12. Minus log of hydronium is this. pH is 2.91. Minus log of hydroxide, that's what we calculated, 11.09. So it's just an exercise in our sets of equations. 10 to the minus 14 divided by either one gives the other. And 10 to the x gives us a concentration. Now this works not at all like this on Blackboard, unfortunately. Blackboard will not let you fill in multiple blanks. It only wants one answer. So, Blackboard, it kind of looks like this. You're given a set of numbers, and you're told one of these is wrong. Which one is wrong? And enter the correct value. Remember, you have to use e-notation, 6.02 e minus 23. Okay, how do we do this? Well, it's actually simpler than you might think. We have a pH and a POH, right? What do we know? Their sum has to be 14. If we actually add these up, we can check to see if one of them is incorrect. If it's 14, then you move to step 2 and calculate H plus and hydroxide. So, 8 plus 8 is not 14, it's 17. So one of these is wrong. The others are right. One of those is wrong. How do we know which one? We have hydronium, 2 pH. Negative log of hydronium is 8.15. Right away you know this guy's wrong. What's the right answer? You take the negative log of hydroxide, get 5.85. That's what you enter on blackboard. So check your sum first. If it's not 14, one of them is wrong. Do this, do that, enter that. Here's our correct values. pH of 8.15. This was correct. This was correct. And this guy is a problem. Any questions? All right. This is my favorite extra credit question. I change the brand of wine every time. But here we have cheap red wine. Calculate the concentrations of hydronium, hydroxide, and the pOH value. We are given the pH. Believe me, you do not want to drink this. Period. Ever. Let's do hydronium. If we know the pH, that's simple. Hydronium is simply going to be 10 to the minus pH. We know the pH, 2.85. 10 to the minus 2.85. Run it through your calculator. You get 1.4 times 10 to the minus 3 molar. Let's do pOH next because it's easiest, okay? Why is it easy? We know pH, we know the number 14. pH plus pOH is 14. No pH. 14 minus 2.85. pOH is 11-ish. And finally, hydroxide. We can do this one two ways. We can take 10 to the minus 14 divided by this. That will give us hydroxide. Or we can take our pOH value, do 10 to the minus pOH. This way, type in your value, minus 11.15. 7 times 10 to the minus 12. Any questions? Well, that's pH. These are the tutorials we have so far. Today we added conjugate acid-base pairs, pH1 and pH2. Now, if you happen to miss it, next week we're doing Chapter 9. After Chapter 9, the following Friday, Saturday, and Sunday, Tutorial 1 and Quiz number 1 will appear back online. This is your opportunity for amnesty. You can do these as often and as quickly as you want. If you need extra credit points, Sunday at midnight, they both go away again. All right, that's it. Thank you so much. I will see you Wednesday. We will do percentage yield on the decomposition of sodium hydrogen carbonate.